Hi there. Welcome to a new video series. This video series is going to focus on the Fourier transform. In this video series, we're going to explain what the Fourier transform is, how it's used, and why it's useful. So we're going to begin this video series by deriving the Fourier transform. So that will take place over the next few videos. The first thing that we need to do in order to derive the Fourier transform is to convert the Fourier series into a complex form. And when we say complex, we mean that we want the Fourier series to contain complex terms, that is, imaginary numbers. So that is the first step that we're going to do in order to derive the Fourier transform. We're going to convert the Fourier series into a series containing complex exponentials. So you would remember from elementary calculus and elementary study of mathematics that complex numbers is basically the square root of -1. And you would have learned about their properties and how you use it and how they're expressed in different forms. And we saw that complex numbers can be written in the polar form. And we designate it by z, and we say that it's equal to r into cos theta plus j sine theta. And you would remember that there's a real term and there's a complex term, and the complex term is the ones associated with j, and you would remember that j is the square root of -1. So the polar form is that this is equal to re to the power j theta. So if you are unfamiliar with this, you can go back to your previous study of maths, the subject, and you can revise it. But it's not really necessary. For now, you can take it for granted that this is the polar form of complex exponentials. So how does this relate to the Fourier series? How can we use this to convert it to the Fourier series? Well, you can see that there's a cos and there's a sine. So what we're going to do is get expressions for cos theta and sine theta, and then we're going to substitute that into the Fourier series. So we're now going to divide both sides by r. And when we do that, we get that cos theta plus j sine theta is equal to e to the power j theta. So now what we're going to do is we're going to write this equation for minus theta. So wherever we see a theta, we're now going to substitute in minus theta. So we have cos of minus theta, then we have plus j sine minus theta. This is equal to e to the power minus j theta. If we remember our trig identities, we would remember that cos of minus theta is just the same as cos theta, and sine of minus theta is just minus sine theta. And this is equal to e to the power minus j theta. So what we're now going to do is that we're going to call this equation, equation 1, and this equation, equation 2, and we're going to add them together. So we're going to take equation 1 and we're going to add it to equation 2. So when we do that, we get cos theta plus cos theta, giving us 2 cos theta, and plus j sine theta minus j sine theta. These just will cancel out, and then what we're left with is e to the power j theta plus e to the minus j theta. And now we're in a position to solve for cos theta. And when we do that, we see that cos theta is equal to a half, since we have divided by 2, into e to the power j theta plus e to the power minus j theta. So in this manner, we have solved for cos theta. So now we can solve for sine theta. How will we solve for sine theta? All we do is we take equation 1 and we now subtract it from equation 2. So cos theta minus cos theta gives us 0, and then plus j sine theta minus j sine theta gives us 2 j sine theta. Of course, a minus and a minus gives us a plus, so it's 1 plus 1 gives us 2. And this is now equal to e to the power j theta minus e to the power minus j theta, and then now solving for sine theta. So sine theta is simply equal to e to the power j theta minus e to the power minus j theta divided by 2j. And now we have solved for cos theta and we have solved for sine theta. So now we can substitute this into our Fourier series and we can get expressions for the Fourier series in terms of complex numbers or these complex exponentials. So if we recall what the Fourier series is from our previous videos on this subject, we would see that we take a function, f of t, and we split it into various trigonometric components. And it was equal to a naught over 2 plus the sum, where we have this number n that starts from 1 and goes to infinity. And we have an as a coefficient multiplied by cos of n omega t. And you'll remember that omega is the angular velocity and t is time. We had done this derivation in the video where we spoke about how to solve the Fourier series for any period. So initially we had expressed the Fourier series just in terms of pi and just in terms of x, and then we had said that series that we had written was only applicable for a period of 2 pi. And then we went and we generalized the Fourier series to be applicable for any kind of period, and we had shown that this is the form we get when we do that. And then the last part of the Fourier series is the coefficient bn, and then multiplied by sine of n omega t. So all we need to do at this stage is substitute in our expressions for cos theta that we had just derived now, and for sine theta, and substitute them into this cos here and this sine here that's in the Fourier series. And of course, instead of theta, we have n omega t. So instead of theta, we will substitute n omega t. So let's proceed with that. So we have a naught over 2 plus the sum 1 to infinity. And we have an, and now we substitute in cos. So we have e to the power j theta. So it'll be j n omega t, j n omega t plus e to the power minus j n omega t, then divided by 2, then plus bn, and now multiplied by what it's equal to in terms of sine. So it's e to the power j n omega t minus e to the power minus j n omega t, and then divided by 2j. Okay, so what we can now do is we can express this term inside the brackets, and what we'll do is we'll take e to the power j n omega t as one common factor, and we'll take e to the power minus j n omega t as another common factor. So when we do that, what we get is what's common. Firstly, we have a n multiplied by e to the power j n omega t. So let's first write that as our first common factor, e to the power j n omega t. So firstly, our term is a to the power n, that's our first term. It's actually a n divided by 2, so we're going to divide by 2. And then we also have bn, so we have bn times e to the power j n omega t, so that's our second term. And this is also divided by 2, and that's also divided by 2. So all we've done is we've taken e to the power j n omega t as our common factor, that multiplied by that, so that multiplied by that, that shows us our first term, and then we have bn times e to the power j n omega t, that's our second term, and then we have taken the exponential as our common factor, and we've taken it out, and then we have just written what's left. I suppose I should also write here that we have to include this j. So we've divided by 2, but we need to incorporate this j. So it's actually bn divided by j. So now we do the same with e to the power minus j n omega t. So when we do that, our first term is a to the power n, sorry, an. And then we have minus, since there's a minus here. And then we have bn divided by j and divided by 2. So this bn over j, we can sort of rationalize that. If we just write it, we have bn over j. So you remember that j is just the square root of minus 1. So if we multiply it by j over j, so what this is equal to is just j bn divided by the square root of minus 1 times the square root of minus 1. And since we're multiplying square root by square root, I mean, that's just going to come off. So we have minus 1 in the denominator. So we can just write it as minus j bn. So bn over j is just the same thing as minus j bn. So we can just substitute that in. We can just write minus j bn. And it's the same here as well. Well, a minus and a minus is going to give us a plus. We can write plus there. And this is just going to give us jbn. So we have essentially an interesting form of the Fourier series at this stage. And we can see that we kind of have conjugates inside this expression. We have an minus jbn here, and we have an plus jbn here. So what we're going to do is we're going to take this first part, an minus jbn over 2, and we're just going to give it another symbol. So we're going to call it cn. We're going to say cn is equal to an minus jbn divided by 2. And the conjugate of this, which is what is in this other expression, we'll just call cn star. And we'll say that is an plus jbn divided by 2. So we can now just simply write this Fourier series that we've just derived here and write it in terms of cn and cn star. So when we do that, of course, we get a naught over 2, and we have our sum. Okay, we have cn. Then we have e to the power j n omega t. And we have c star n. And we have e to the power minus j n omega t. So what we're going to do now is we're going to split this sum. We're going to split the sum since it's just these two terms that are within the sum. So what we're going to do is split it, okay? We're going to remove the bracket here. So we have sum of n to 1 to infinity, and we're just going to bring the plus a little bit more in the front, and we're going to write this sum here as well. And of course, it goes from 1 to infinity. So the next thing that we're going to do is just a little bit of trickery, right? In terms of this limits, in terms of this sum. We can see that the only difference between this term here and this term here is that there is a negative in front of this exponential, minus j here and plus j here. And of course, there is some difference with these coefficients. So we can make this second term look the same as the first term. So how would we do that? Well, what we would do is that if we look at this minus jn, okay, so we're saying that n is positive numbers from 1 to infinity, and there's a minus n here. So what we could simply just say is that we could now, well, we could keep everything as it is here and just make a little change, that last expression. We have our sum, and now we have e to the power j n omega t. So we've changed it to this positive, right? We've changed the sign, and we have minus n. So we've now changed it to a plus here, right? So in order to keep everything consistent, all we can do is that we can just say n is all negative numbers. It's the same thing, right? So instead of saying n is all positive numbers and there's a minus in front, we could just change this to a plus, and then we could say, no, n should only be negative numbers. So n will run from minus infinity to minus 1. So n is all negative numbers, and it's the same thing. Here we have minus n is all positive numbers. We change the sign to a plus here, and we say n is only negative numbers. So it's literally the same thing. And since we have done that, this also now becomes from Cn star to Cn. If we think about what the difference is, it's only in terms of Bn. We have minus jbn and we have plus jbn. And what is Bn associated with? Bn is associated with sine. So since now sine of minus n is literally going to change the sign, since sine of minus theta is simply equal to minus sine theta, which we have already said before, it's literally going to be the case that this plus will now also become a minus in terms of Cn star. So that's why Cn star becomes Cn. So if we just look at what we have thus far, we have n, right? And let's look at the boundaries of n in terms of what we have written. We have n going from minus infinity to minus 1, and then we have a value for where n is equal to 0. And then what's left? We have n going from 1 to infinity. So what does this mean? It means that n just goes from minus infinity to positive infinity. So we could replace this entire 3 terms to be just one term, to be just one sum where n goes from minus infinity to positive infinity. And remember, what's inside the summation is the same in these expressions. So we are allowed to do that. So if we do that, what we get is that ft is equal to the sum where n goes from minus infinity to positive infinity of Cn e to the power j n omega t. So this is the Fourier series written in terms of this complex exponential. And if we were to try to write functions in terms of this form of the Fourier series, all we would need to do is just find this coefficient Cn. And it's quite easy to show that Cn is just equal to 1 over the period, the integral from whatever the period is, 0 to t, or minus t over 2 to plus t over 2. Whatever the function is, multiplied by e to the power minus j n omega t dt. So if we wanted to find the Fourier series of some kind of function, we would just need to find this coefficient Cn, and this is what Cn is equal to, and we would proceed in the same manner as before. So as I said previously, this is all leading us to the derivation of the Fourier transform. So this conversion of the Fourier series to be in terms of this complex exponential is the first step to finding the Fourier transform. So thank you very much for watching.